Do you know the lowest temperature humans have ever created? It's about minus 273.149999999 degrees Celsius, just a billionth of a degree above absolute zero. And yet, that tiny fraction is a boundary we can never cross. This isn't a matter of technology, it's a rule of the universe. Albert Einstein would say it's impossible. Quantum mechanics agrees. And the third law of thermodynamics essentially seals the verdict. Why? Because reaching absolute zero would require infinite energy. Even burning through the entire sun wouldn't be enough. Still, scientists refuse to give up. Using lasers, magnetic fields, and methods you might never imagine, they've pushed temperatures lower and lower, uncovering a world that completely overturns our intuition. In that realm, gases become a fifth state of matter. Atoms begin to act collectively. The rules of physics start to look very different. Absolute zero has become a window into the deepest nature of reality. So here's the question. Where does minus 273.15 degrees Celsius come from? Has anyone ever actually measured it? The answer is no, it was derived mathematically. In 1802, a French scientist, Joseph-Louis Gay-Lussac, conducted a simple experiment. He put gas into a graduated container and cooled it down step by step. He discovered that for every degree drop in temperature, the gas's volume shrank by about 1/273. This implied something remarkable. If you kept cooling at minus 273.15 degrees Celsius, the volume would reach zero. But that can't happen. Matter can't simply vanish. So this temperature was interpreted as a fundamental limit, the lowest possible temperature. Later, it was named absolute zero. But here's where it gets even more interesting. What is temperature really? At its core, temperature is the motion of particles. When you feel heat, it's because atoms are vibrating intensely. When you feel cold, those vibrations slow down. Absolute zero would mean all motion stops. Everything becomes perfectly still, silent, and frozen. Sounds simple, right? But there's a paradox. Quantum mechanics tells us that particles can never be completely at rest. According to the Heisenberg uncertainty principle, you cannot know both the exact position and velocity of a particle at the same time. If a particle were perfectly still, its velocity would be exactly zero, something you could know precisely, which violates this principle. So even at absolute zero, particles retain a tiny amount of motion, called zero-point energy. It's like a sleeping person whose heart never truly stops beating. The universe does not allow perfect stillness. So how close can we get? In 2021, German physicists set a record by cooling a quantum gas to just 38 trillionths of a degree above absolute zero. They achieved this in a 120-meter tower, letting atoms fall freely in microgravity while carefully controlling magnetic fields to suppress expansion. At that temperature, atomic motion is slower than a snail by a factor of a trillion. And yet, even then, they didn't cross the line. This leads to another question. Why does temperature have a lower limit, but no real upper limit? The highest possible temperature is the Planck temperature, about 10 superscript 3 superscript 2K. The reason lies in asymmetry. High temperature means faster particle motion, kept by the speed of light. Low temperature means slower motion, bottoming out at zero. But these two limits are not symmetric, so the range of temperature in the universe is inherently uneven. Now imagine something unsettling. What if your hand touched a piece of metal at absolute zero? You wouldn't feel the cold immediately. Your nerves need time to respond. But before you could react, damage would already be underway. The water in your cells would freeze instantly, forming microscopic ice crystals that tear cell membranes apart. Blood vessels would constrict, cutting off circulation. Tissue would begin to die. You might even hear a faint sizzling sound. Not from heat, but from extreme cold. Your skin could stick to the surface, like a tongue on frozen metal, but far more violently. Trying to pull away would cause severe tearing. By the time you reached a hospital, doctors might tell you the hand cannot be saved. And yet, within this terrifying cold lies some of the universe's greatest wonders. In 1995, scientists created a new state of matter and won the Nobel Prize, the Bose-Einstein condensate. Using lasers and magnetic fields, they cooled atoms to just 170 nanokelvin above absolute zero. At that point, something extraordinary happened. Individual atoms lost their identities and behaved as a single quantum entity. Thousands of atoms moved as one, like a crowd suddenly marching in perfect unison. Even stranger phenomena appear. In 1938, scientists discovered superfluidity, liquid helium cooled below minus 271 degrees Celsius flows with zero viscosity. It can climb container walls and slip through the tiniest cracks. More recently, in 2024, physicists in the US and the Netherlands created a molecular Bose-Einstein condensate, where over 1,000 molecules occupy the same quantum state. These breakthroughs hint at future technologies, superconductors with zero resistance, or quantum computers millions of times faster than today's machines. Interestingly, nature has its own ultra-cold laboratory. The Boomerang Nebula, about 5,000 light-years from Earth. Its temperature is around minus 272 degrees Celsius, even colder than the cosmic microwave background. This happens because gas expelled from a dying star expands rapidly, losing heat as it does so, until it becomes colder than the surrounding universe. And then there's an even more unsettling idea: the ultimate fate of the universe. Scientists predict that after about 10 superscript 1 years, the universe may undergo a big freeze. Stars will burn out. Black holes will evaporate. No new structures will form. The temperature of everything will drift ever closer to absolute zero. Motion will cease. Chemical reactions will stop. Time itself will lose meaning, because nothing will happen to mark its passage. Entropy will reach its maximum. Total disorder, yet perfect stillness. That's the true terror of absolute zero. It's not just a temperature. It's the end of all processes, the opposite of existence, a boundary where time, motion, and life all fade away. And yet, humans keep pushing toward it. In 2025, researchers at the Chinese Academy of Sciences developed a new material, potassium hexafluorophosphate, capable of cooling across a wide temperature range from room temperature down toward near absolute zero, potentially transforming refrigeration technology. Meanwhile, the Cold Atom Lab aboard the International Space Station continues to create some of the coldest matter ever produced, taking advantage of microgravity to reach lower temperatures for longer durations. Every step closer to absolute zero reveals a bit more of the universe's underlying code. We may never reach it, but that's exactly what makes the pursuit meaningful. Like Sisyphus pushing his stone, we keep going, knowing the goal is unattainable. Along the way, we discover new states of matter, new quantum phenomena, and new technologies that reshape our world, from MRI machines to quantum computing. So how terrifying is absolute zero? It can freeze motion, freeze time, freeze possibility itself. It is both an ending and a beginning, a forbidden boundary we can never touch, yet will never stop chasing.